Hi everyone, welcome to our physics class. Today I am going to discuss about the fifth very important 5-mark derivation in electric charge and electric field. So that is electric field at a point due to a uniformly charged infinite plane sheet. Okay, so let's start today's class. So this is very important for 5-mark derivation of expression for electric field at a point due to uniformly charged infinite plane sheet. Okay, first here, let us consider uniformly charged infinite plane sheet. Okay, so this is a plane sheet. Suppose the electrons are removed from this sheet. So what happens? It will get positively charged, right? The electrons are removed from the sheet, so it will get positively charged. So that is uniformly spreads over the entire surface of the sheet. So that is actually surface charge distribution. If a charge spreads over two-dimensional surface in space, that is the surface charge distribution. So here this is x-axis and this one is the y-axis and this is z-axis. So this is the origin. So here this is lies in YZ plane. So this is infinite plane sheet. So lies in YZ plane. Actually Y goes to infinity, even Z goes to infinity. Okay. So now we can choose the two observation points. One is P and another one is P dash. We can choose the two observation points P and P dash. So P and P dash are two observation points, and these 2 points are equidistant from a uniformly charged sheet. Okay, so now we can imagine a Gaussian cylinder taking P and P dash, so that is the axis. So this is the axis of the imaginary Gaussian cylinder. So this is the point P. Now we can choose imaginary Gaussian cylinder. So this is the imaginary Gaussian cylinder. So taking P and P dash, so that is the axis of the imaginary Gaussian cylinder. So Gaussian cylinder having the uniform cross-sectional area. So that is A. Okay. So now let us consider the distance from sheet to the observation point P. So the distance from sheet to the observation point P. So this is R, and the distance from P dash to the uniformly charged sheet, and this is also R. So here the point P and P dash are equidistant from the sheet. So this is the point P. So this is P dash, right? So first here we have to consider a sheet. Suppose if the electrons are removed from the sheet, so what happens? The sheet gets positively charged. So we have to find out what amount of electric field that is produced by uniformly charged infinite plane sheet. So here we have to choose the two observation points. One is P and another one is P dash. So P and P dash are equidistant from the sheet. Okay, distance from sheet to P and sheet to P dash. So both are same, that is R. So after that, here we have to choose an imaginary Gaussian cylinder taking P and P dash. So that is the axis. Okay, so P and P dash. This is the axis of the imaginary Gaussian cylinder. So this is imaginary Gaussian cylinder. So P and P dash. So this is the axis of this imaginary Gaussian cylinder having a uniform cross-sectional area. So that is A. So it is having the uniform cross-sectional area. So that is A. A is the uniform cross-sectional area of the imaginary Gaussian cylinder. Okay, right? So after that, we have to mark the direction of electric intensity at point P and at point P dash. So how do you find out the electric intensity at a point? So by using test charge. So a unit positive test charge plus Q naught is placed at the observation point P. So due to this uniformly charged plane sheet, so plus Q naught will experiences the repulsive force. So this is the direction of electric intensity at point P. So again, so plus Q naught that is placed at the observation point P dash. So due to this uniformly charged sheet, so again plus Q naught will experiences the repulsive force. So this is the direction of electric intensity. And so what is the direction of normal? So that is also very important here. So here the direction is away from the sheet. So what is the meaning of normal? Normal is imaginary perpendicular to the given surface and it is always directed outwards. So here is also the normal is directed outwards, right? So this is the direction of normal. That means A vector. So this is A vector and this is A vector and this is the direction of electric intensity and this is the direction of electric intensity. So electric intensity is directed away from the uniformly charged infinite plane sheet. Okay, so now we can choose a small surface area on the Gaussian cylinder. So what is the direction of ds vector? So this is ds. So ds is a small surface area. So what is the direction of ds vector? So ds vector, that is radially outwards, right? So what is the direction of electric intensity at this point? So plus Q naught is placed at this observation point due to this uniformly charged plane sheet. So plus Q naught will experience a repulsive force. So this is the direction of electric intensity. So this is the direction of electric intensity. So this is E vector. Okay, so what is this? This is ds vector. Okay, so this diagram is very, very important. So now first, let us consider the surface charge density. That means charge per unit area. Okay, surface charge density is charge per unit area, right? So the total charge enclosed by this imaginary Gaussian cylinder is the total charge enclosed by the imaginary Gaussian cylinder is Q is equal to sigma into A. So call this as equation number 1. Okay, what is this? The total charge enclosed by imaginary Gaussian cylinder. So after that, we have to calculate the total electric flux through the entire Gaussian cylinder. So the total electric flux through the Gaussian total electric flux through the Gaussian cylinder is total electric flux through the Gaussian cylinder, that is equal to flux linked with the left flat circular surface, flux linked with the right flat circular surface, and flux linked with the curved surface, right? So total electric flux, that is equal to flux linked with the left flat circular surface. Flux is measured by taking the dot product of two vectors, that is electric field vector and the area vector. The flux linked with the right flat circular surface, that is E vector dot A vector, and flux linked with curved surface. So here actually we are choosing just a small surface area. So that is why so flux linked with the curved surface is integration of A vector dot ds vector. Okay, so total electric flux, that is equal to, so dot product of two vectors, that is given by the product of magnitude of two vectors and cosine of the angle in between them. So what is the angle between E vector and A vector? Both are moving in the same direction. The angle in between them is 0. So this is EA cos 0, right? So EA cos 0 is 1. So here is also the flux linked with the right flat circular surface is EA cos 0, because here is also the angle between E vector and A vector is 0, because both are moving in the same direction, right? So this is EA cos 0 is 1, plus the integration of dot product of two vectors, that is given by the product of magnitude of two vectors, that means the magnitude of E vector, magnitude of DS vector, and the cosine of the angle in between them. So what is the angle in between E vector and DS vector? That is 90 degree. So this is 90 degree. So cos 90. So cos 90, so that is equal to 0. So this term goes to 0, right? So then we will get total electric flux, that is equal to EA plus EA plus 0. So total electric flux is equal to EA plus EA, that is 2 times EA. Okay, so now we have to apply the Gauss's law. Okay, so now apply the Gauss's law. So what is the statement of Gauss's law? The total electric flux through any closed surface, that is equal to 1 over epsilon naught times the net charge enclosed by the closed surface. So call this as equation number 3. Okay. So this is equation number 2. Now the equations 2 and 1 in equation 3. Substitute the equations. Substitute equations 1 and 2 in equation 3. Okay. Equations 1 and 2 in equation 3. So then we get, what is the value phi? So phi is 2 EA, right? That is equal to Q is sigma A divided by epsilon naught. So A cancels here. So E is equal to sigma divided by 2 epsilon naught. So what is this? The expression for electric field at a point due to a uniformly charged infinite plane sheet. Actually, electric field at a point due to uniformly charged infinite plane sheet does not depend on the distance from observation point to uniformly charged sheet. So electric field here does not depend on the distance from observation point to uniformly charged plane sheet. So in vector form, so this equation, so that can be written in the form of E vector is equal to sigma divided by 2 epsilon naught into n cap. So where n cap is a unit vector, so directed away from uniformly charged plane sheet. So what is the direction of electric field here? So directed away from uniformly charged infinite plane sheet. Okay, so this derivation is very important for 5 mark. Okay, so thank you.